Hey everybody. So I'm going to use this lecture to talk a little bit about the binomial and related distributions, as well as the Poisson distribution and its related distributions. So just in general, the binomial distribution is appropriate for situations where you have events occurring in kind of quantiles. So maybe you've divided time up into years, so each year is a separate trial, and then you can either have an event occur or not occur in a given trial. So that's appropriate. When that's appropriate, you would use the binomial distribution. For the Poisson distribution that we'll be talking about, basically, we're not assuming that say, time can be broken up into equal intervals. Basically, we allow the possibility that an event can occur anywhere in time or maybe space. And so anyway, there's slightly sort of mathematically different formulations, and anyway, there's cool problems that we can solve using both approaches, and we'll be talking about those today. All right, so let me go ahead and get my screen share going. Okay, so so let's just do a quick review. You may remember that the binomial distribution, we have, of course, probability mass functions as well as CDFs for the binomial distribution. And the basic idea is that we're going to have some fixed number of trials, say little n, and we define a random variable, in this case x, for the number of occurrences of some event we're interested in over that number of trials. And we can talk about a very specific realization of this random variable, big X. And we can also talk about the probability of one of these events actually occurring in any particular trial. So that would be P, and of course, the probability of the event not occurring in a particular trial is going to be 1 minus P. And what we found when we worked out the math was that the probability mass function for the binomial distribution here, probability that the random variable is going to be equal to some specific number of occurrences of an event given n trials, and the probability of P per trial is equal to the binomial coefficient indicated here. Again, we've got the number of trials and the number of occurrences of our event of interest, times the probability that the event will occur in a given trial raised to that number of trials we're interested in, little x, times 1 minus P, the probability that we won't have the event raised to the rest of the trials, which is going to be n minus x. This binomial coefficient, remember where it comes from? It's just basically telling us the number of different combinations of sequences in which you can have x occurrences in n trials. And so that binomial coefficient is just given here, where we have n, or x is n factorial divided by x factorial times n minus x factorial. Okay, so we've been over all of that and gone through a number of problems. So again, this is the probability mass function for the binomial distribution. The corresponding CDF, of course, would be the case where we're looking for the probability that the random variable is less than or equal to that little x, or a specific number of realizations, or a specific realization for the number of occurrences, again, given n trials and probability of P. And of course, that's just going to be our cumulative distribution function, CDF, of the binomial distribution. And what we do is we take that PMF and we sum it from no occurrences, that's k equal to 0, up to x occurrences, little x. And of course, then, because we're talking about the occurrences being summed here, we're going to replace little x here with k in the sum. And so you see k appearing where x appeared in all of these terms. Okay, and then we can talk about a very specific sequence in which basically we are interested in the probability that on the nth trial, we will get the first event occurring. So that's what the geometric distribution gives us. And so the probability mass function for the geometric distribution, again, is going to be that random variable for the number of trials to the first event equals some specific number of trials, little n. And that's just going to be P, since we only have one event in this particular scenario, with probability p, so we only have p to the 1 power here, times q, that's the probability of non-occurrence, which of course is 1 minus p, raised to all of the other trials preceding the nth trial. So that's why we have essentially 1 minus p raised to the n minus 1. So that's the probability mass function for the geometric distribution. And of course, the corresponding CDF is going to be the probability that that random number, random variable, sorry, n, of trials to the first occurrence is less than or equal to some specific number n. We can pull the p out because it isn't raised to anything that would keep it in the sum. And then we have the sum of occurrences, I'm sorry, of trials from I equals 1 to n. And again, the thing to keep in mind is, and we talked about this in class, that the random variable here for the geometric distribution is different than the random variable for the binomial distribution. So the random variable for the geometric distribution is basically the number of trials until you get the first event, right? That's what that big N stands for. Whereas the random variable in the binomial distribution is the number of events, come up here, sorry, is the random variable for the number of events you will have in n trials given a probability of p. So just keep that in mind. That explains also why the summation indices here are different for the geometric distribution. We're going from I equals 1 to little n compared to the binomial distribution k equals 0 to x. In this case, for the CDF from the binomial, we can have a non-occurrence that is a perfectly valid outcome for the random variable for the number of occurrences. And so that would correspond to k equals 0 here. Whereas in the geometric distribution, we'll have to have at least one trial, and it'll have to be, the smallest n can be is 1 to get that event occurring, that first event occurring. Okay, so, and then I shared with you this kind of cheat sheet for the kind of questions that go with each of the different PMFs and CDFs we've talked about. So if we are talking about a binomial PMF, that would be appropriate if the question goes something like, what is the probability of X occurrences in N trials? Because basically what we're allowing for here is the possibility that those X occurrences come in any order. And so we have to account for the fact that they would occur in any order. And that's what the binomial PMF does for us. Similarly, if we were asking the question, what is the probability of X or fewer occurrences in N trials? Well, now we're really talking about a binomial CDF because we're tracking the probability of not just X occurrences, but X minus 1 occurrences, X minus 2 occurrences, and so forth. We're summing up over all of those possibilities. On the other hand, for the geometric PMF, the question we might apply that particular distribution for would be like this. What is the probability of a first occurrence after N trials? Okay, so and again, the key thing here is that there is only one sequence that gives us a first occurrence after N trials, and that's basically N minus 1 non-occurrences followed by an occurrence. So that would be the geometric PMF. The corresponding geometric CDF is what is the probability of a first occurrence after N or fewer trials. And again, each of these sequences in the sum is going to be unique because we will have a series of non-occurrences and then we'll end with an occurrence. And so then it's really just that we have N or fewer trials associated with each of those terms in the sum. So we also talked a bit about the negative binomial distribution. And so it's just kind of an elaboration on the geometric distribution. And it allows us to determine how many trials, what is the probability that we're going to get the kth event on, say, after N trials. And so let's be specific here. Let the random variable big N sub k represent the random variable for the number of trials to the kth occurrence. Okay, so the number itself, the random variable itself, is going to be number of trials, but now we're looking at the kth occurrence, not just the first occurrence like we did in the geometric distribution. If the probability of each event is statistically independent, then the PMF for this random variable is governed by what's called the negative binomial distribution, and that's shown here. I'm going to rather than talk about this distribution in detail here, I'm going to actually derive it for you. So let's figure out where that comes from. And basically, it's very kind of simple logic problem. If the kth occurrence occurs on the nth trial, which is kind of what we're talking about for the negative binomial distribution, that necessarily implies that there were k-1 occurrences in the previous n-1 trials, right? And because these k-1 occurrences can occur in any order, we're really talking about the probability of this happening being estimated by the binomial PMF, which allows for all of those k-1 occurrences to essentially occur in any order over n-1 trials. And so if we just write out the probability for k-1 occurrences over n-1 trials, that's again the binomial PMF. So we're letting the random variable for the number of occurrences in n-1 trial, we're letting that be equal to k-1. And then that's just going to be the binomial PMF. So we have the binomial coefficient, where we're basically looking at n-1 trials and k-1 events. And then we have the probability associated with those k-1 events times the probability of a non-occurrence for the rest, which is n-k. We also have to put that the probability is going to be 0 if the number of trials is less than k, because obviously you can't have k occurrences in fewer than k trials. And furthermore, the probability that we will have just one more occurrence on the nth trial is going to be p, right? Because these are statistically independent events. And therefore, we can say that the probability for the random variable n sub k equal to n is just going to be p times that probability that we just derived from the binomial distribution. And so when we factor that p in, let me just go back a second. So we had a p raised to the k-1, and we multiply that by p, that -1 goes away, and that is our negative binomial distribution. So again, if we wanted to estimate the probability associated with the kth event occurring after n trials, this is how we would compute that, that estimate. Okay, so let's just kind of quickly summarize then where we've been, and then that'll kind of set up for where we're going. So we have the binomial distribution PMF, which looks like this. Again, looking at a random variable for the number of trials, the number of occurrences in n trials given the probability p per trial. And then we talked about the geometric distribution as being kind of a special case of the binomial distribution, in which we're really interested in the number of trials to the first event. And so that random variable then is the number of trials to the first event. And here it's being set to a specific number, specific realization, little n. And then we could furthermore generalize the geometric distribution to the negative binomial distribution PMF, which is essentially the number of trials to the kth event. And so it looks like this here. That's the negative binomial distribution. So that's the relationship between the binomial distribution, the geometric distribution, and the negative binomial distribution PMFs. And of course, you can write down corresponding CDFs for each of these. And remember, the binomial distribution, basically what we're doing is we're taking some maybe time, or space, and we're dividing it up into trials, which are discrete units. And then we're asking, did we get an event, in this particular time interval, or did we not get an event in that particular time interval? So those are the trials. In this case, would be the delta t time intervals. So the alternative might not be time, it might be, I don't know, pieces of equipment or samples collected at the beach. Either those samples pass a standard or they don't pass a standard if you're talking about water quality. So that is a binomial distribution. That's kind of its origins and what it's applied for. On the other hand, we can imagine a situation where we were interested in evaluating the number of events that occur over some continuous amount of time, say within 24 hours. So those events could occur anywhere in that 24 hours. They might occur right next to each other, or they might be really spread apart. We don't know. Maybe we don't even really care how they're distributed over that 24 hours. We just want to know what is the probability that we're going to get 5 events in that 24-hour period? And likewise, we could have the same thing for space. Maybe we're interested in understanding the number of events that occur over a certain distance. And so we could, of course, apply the binomial distribution to these problems. We'd have to divide up the time or the space into equal increments and then, apply our theory that way. But again, that might be really artificial if there are no obvious sort of discrete units of time or space here. And so that's what the Poisson distribution is for. Basically, it's an elaboration of the binomial distribution in the case where an event can occur at random at any instant of time or any point in space. And we make a couple of other assumptions. Basically, we assume the occurrence of the event in a given time or space interval is statistically independent of that in any other non-overlapping interval. So even though we're talking about continuous time or space, we could divide those time and space regions into intervals and then look at whether the events in each of those intervals was statistically independent. And the Poisson distribution would assume that they are statistically independent. And furthermore, we're going to assume that there's a mean occurrence rate nu of an event occurring over, say, some time or space. And so that would be like the number of events that occurred in 1 hour on average. And furthermore, we're going to assume that that mean occurrence rate is constant, it doesn't change with time. And furthermore, the probability of 2 or more occurrences exactly the same time or location is negligible. So we're not going to consider that kind of extreme situation. And basically, when we make these assumptions, we can write out the Poisson distribution. The Poisson distribution is sort of consistent with that set of assumptions. And basically what it's saying is, this is the PMF version, that the probability that our random variable for the number of occurrences x that occur in a given amount of time t is going to be some specific realization, little x, is going to be nu, remember that's our mean occurrence rate, times the time interval of interest raised to the x over x factorial times e to the minus nu t. And of course, we could write out the corresponding CDF, which is just going to be that the random variable x is less than or equal to some specific number of occurrences, little x. And then we're going to sum, because we can go from non-occurrence, so no occurrence at all, p equal to 0 to x, again, over that fixed amount of time. So we're just plugging in our Poisson distribution into that sum to get the CDF. And it can be easily shown that the expected value of x for this distribution is equal to the variance and is equal just to nu t. So I just showed you what the Poisson distribution is, but we can learn a little bit more about it by showing at least one derivation, which is based on a sort of a limit of the binomial distribution. And that kind of gives us a better sense of how the binomial and the Poisson distribution are related. So if you wanted to know the probability that there would be x events in time t, given some average number of occurrences, say lambda equals nu times t in time t, we could actually tackle this problem as a Bernoulli trial. So what we would do is we would divide up that time t into n equal intervals, and then we would note that the probability of occurrence of an event occurring in any interval is just going to be the average number of occurrences in time t divided by the number of intervals we have for that time t, which would be n. So our probability then in a binomial trial is going to be lambda over n. And then, of course, the probability that the event will occur x times within the n trials can be calculated from the binomial PMF. So we're looking at the probability that our random variable n in this case, I think we called it x previously anyway, equals little x in n trials is just going to be the binomial coefficient, n over x, times the probability of an occurrence, which is going to be lambda over n, we already established that, raised to the x, times the probability of a non-occurrence, 1 minus that probability of occurrence raised to the rest of the sort of trials, the n trials, n minus x trials. And so what we're interested in then kind of assessing is what happens if we let the number of intervals in that fixed amount of time, we let that n go to infinity. So we take this probability that we're going to get x occurrences and n trials from the binomial distribution, and then we let the number of intervals go to infinity. And the claim is going to be that basically when you do the math, you end up with the Poisson distribution in the end. So you can sort of see the Poisson distribution then as a limit in which the binomial distribution goes to an infinite number of intervals or infinite number of trials over some fixed amount of time. Okay, so let's actually work out the math of that. So what I'm doing is I'm basically taking this quantity here, this limit, and I'm moving it over to the next page. So that's what we're seeing here. And then I can play with this a little bit. So I can go ahead and write out the binomial coefficient. It's going to be n factorial over x factorial times n minus x factorial. And everything else I think is the same here. And next I want to do a little rearranging. So I'm going to take n to the x and I'm going to move it out toward the front of that denominator. And then I'm going to move the x factorial together with the lambda to the x. The reason I would do that is because then the lambda to the x over x factorial has nothing to do with n, and so that can actually come out in front of the limit eventually. What I'm left with here is I've got, let's concentrate on this term here, I've got n factorial over n to the x times n minus x factorial. So let's kind of expand that out. So n factorial is going to be n times n minus 1 times n minus 2, dot, 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 to n minus x plus 1. Now, what happened to all of the smaller terms? Well, basically, once I get to n minus x factorial, I can cancel that expression in the numerator and the denominator because we have n minus x factorial in the denominator here. So everything past n minus x factorial just canceled with the denominator. And then if I think about it, I've got exactly x terms here. I've got 1, 2, 3, and then I've got x terms because I stop before n minus x. And that means I can divide, or not divide, but sort of distribute this n to the x so it's associated with each of these terms. And I went ahead and did that here. And furthermore, I can then divide the n in the denominator into all these terms in the numerator, and I end up with, and then also pull out this lambda x to the x factorial in the front because it doesn't depend on n. And then I end up with a product of a series of terms that involve things like 1 minus 1 over n, 1 minus 2 over n, 1 minus x minus 1 over n, etc. And all of these terms basically are going to go to 1, right? Because as n goes to infinity, this term here is going to go to 0. So we have 1 minus 0 or 1. Same thing here. We're going to have 2 over infinity, which is 0. So we'll have 1 and so forth and so on. So basically, all of these, and there should have been a dot, dot, dot here. Sorry about that. All of these terms involving the the ratio of, say, n minus 1 or n minus 2, dot, 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 divided by n, are all going to go to 1 as n goes to infinity. And actually, that's true for this term here as well. Now, I've taken this 1 minus lambda over n raised to the n minus x, and I've written it as a product of that same quantity 1 minus lambda over n raised to the n and then raised to the minus x. And in this case, basically, as n goes to infinity, lambda over n is going to go to 0, and then 1 raised to any power is just 1. So in the end, what we end up with is lambda to the x over x factorial times what's left of that limit, which is really just limit as n goes to infinity of 1 minus lambda over n to the n. And you guys might recognize this as essentially the definition of the exponential. If we isolate minus lambda here, this thing here is exactly equal to e to the minus lambda. And so, so this limit basically evaluates as lambda to the x over x factorial times e to the minus lambda. And if we think about it, lambda is just equal to nu times t. It was the average number of occurrences in time interval t. That's how we define lambda. And that's going to be, by definition, equal to the mean occurrence rate, the number of occurrences on average per unit time times time. And so substituting nu t for lambda, we get exactly the Poisson distribution. And so we've then shown, coming back here, we basically have shown then that if you take the binomial distribution and you let the number of intervals in a fixed amount of time go to infinity, you recover the Poisson distribution. Okay, so so we have the Poisson distribution, which is kind of like the binomial distribution. Instead of discrete trials, we have this like continuous variable that we're evaluating occurrences over, say, time. What is the equivalent of the time to a first event or a first occurrence, just like we had for the geometric distribution when we were looking at trials? Well, that would be the exponential distribution. And we've actually talked about the exponential distribution before, so now we're just bringing it back in a very specific context related to the Poisson distribution. And we can sort of establish this relationship between the time to a first occurrence and the exponential distribution using the following set of logic or set of ideas. So let T1 be the random variable for the time to a first event. Okay, so just like for the geometric distribution, capital N was the random variable for the number of trials to the first event, we're going to let capital T1 be the random variable for the time to the first event. And then if we were interested in the probability that that random variable was greater than t, basically that would be the probability that the first event has not occurred, because this is our realization here, little t, and if the time to the first event is greater than little t, then basically what we're saying is that that first event has not happened yet. We can write out that the probability of the random variable t1 being greater than t is equal to the probability that there are no events, that is our random variable for the number of events equals 0 given time t and a mean occurrence rate of nu. And if we plug that into the Poisson distribution, that's going to be nu t to the little x, which is 0, divided by x factorial, which is 0 factorial, or 1, times e to the minus nu t, which then just equals e to the minus nu t. And this is the really cool bit. Of course, we can take the complement of this. So the probability that first occurrence is less than or equal to a specific value of t is just going to be 1 minus this probability e to the minus nu t. It's the complement. And that, if you look at it, is the CDF for the occurrence of the first event. We're basically asking what is the probability that our random variable for the occurrence, the time to the first occurrence, is going to be less than or equal to some specific value, which by definition is the CDF. And then if we were interested in the corresponding PDF, of course, all we have to do is take the derivative of the CDF with respect to t. And that's going to pull down a minus nu here, and the minus and minus nu, those minuses cancel. So the corresponding probability density function for the time to the first event is going to be nu times e to the minus nu t. That's kind of a really cool thing. You know, if you think about it, the Poisson distribution is a probability mass function because we're counting the number of events in a given amount of time, right? That's kind of what it's telling us. But when we compute the corresponding exponential distribution, which is going to give us the time to the first event, it becomes a probability density function because we're not really, our random variable isn't discrete anymore. It's a continuous random variable. Whereas if you looked at the, sorry, let me go back for a second. If you look at the Poisson distribution, boy, we have to go way back. Somewhere here. There we go. If we looked at the Poisson distribution, this is actually a PMF because we're asking, what are the number of occurrences, and those are numbers like 1, 2, 3, 4, 5, and so on, that are going to occur in a given amount of time, given a mean occurrence rate. So even though the Poisson distribution is a discrete PMF, I'm just kind of winding my way back to where we were here. Even though the Poisson distribution is basically a discrete distribution, and so we talk about a PMF, not a PDF, the corresponding exponential distribution for the time to the first event is a continuous probability distribution, and therefore a PDF. And that kind of makes sense because we know that the exponential distribution is a continuous distribution. And then if I think we went through this in detail in one of the other online lectures, but we can, compute the mean from the expected value of that T1, and it just works out to 1 over the mean occurrence rate. So that's the continuous version then of the geometric distribution. Okay, so let's kind of map out where we've been. Remember this slide? So basically we have, if we've got discrete time or space, or we've got countable items like the number of samples again that we've collected. These are trials, specific trials. We've got the binomial distribution PMF and CDF, the geometric distribution PMF or CDF, and the negative binomial distribution PMF or CDF. And then if we've got continuous time or space, and we're not talking about discrete trials anymore, but we're interested in events occurring over some continuous time or space, we've got the Poisson distribution PMF, which is going to tell us how many events we're likely to get in time t given a mean occurrence rate of nu. And then we also have the exponential distribution, should be PDF, sorry about that, which is going to be the probability that we get our first event after a time t, and that's just nu e to the minus nu t. And it turns out that if we're interested in the time to the kth event, just like we had with the negative binomial distribution, we can write out a corresponding distribution for a sort of continuous time, and that's going to be the gamma distribution. And again, this should be PDF. So I'll correct that when I upload the notes. So this should be PDF and this should be PDF. And that's going to look like this. It's called the gamma distribution. And K here is essentially the number of events that occur in time t. So this is the probability that the time to the kth event is equal to t, given a mean occurrence rate of nu. And we can derive the geometric distribution from the Poisson distribution as follows. Another cool little derivation. So let's define tk as the random variable for the time until the kth event, basically what we said on the last slide. Then the probability that tk is going to be less than or equal to some specific realization of little t is the probability of k or more occurrences in time t. So basically what we're saying is that the time to the kth occurrence is less than or equal to little t. So that means it's got to be equivalent to the probability that we're going to have k or more occurrences in that time t. Hope that made sense. It made sense to me. And so we can actually write that out in terms of the Poisson distribution. So this probability that tk is less than or equal to t is just going to be the probability that we get exactly x events in time t, where x is going from k to infinity. And of course, that's going to be 1 minus the complement. So that's the probability that we get x events in time t running from x equal to 0 to k minus 1. So I'm just taking the complement of this guy here and making it 1 minus. And so this is a CDF for the probability that of time to the kth event, right? Just by definition, that's the CDF for tk. So if I want the PDF, I just simply take the derivative of that CDF. And when I take that derivative, lo and behold, I get the PDF. Again, it should be PDF for the gamma distribution. So that's going to be the probability that the time to the kth event is equal to little t. Now, if you are super diligent and you actually try to carry out that derivative, you'll notice that it looks extremely non-trivial. In fact, I started to do it by hand and then eventually I gave up and then went to Mathematica, and Mathematica told me this is the correct answer. So, so anyway, this is our PDF for the gamma distribution. Oops, so I was kind of going. And so anyway, we'll finish up here, and hopefully you've got this sort of sense of a parallel between the situation where you kind of divide whatever you're thinking about into individual trials, and that's where you're going to be applying the binomial PMF, or perhaps the geometric PMF, or maybe the negative binomial PMF, depending on the kind of question that you're trying to answer. Or you could have the thing that you're thinking about essentially be a continuous case where you've got maybe a certain amount of time or a certain distance of space where you're interested in events occurring. And that would be the situation where you would use the Poisson distribution, or the exponential distribution, or the gamma distribution, and then go from there. So we'll cover some examples of this in class tomorrow, and thank you very much for listening. See you later.